Hello and welcome to lesson number 6 in Unit 6, Solving Problems with Quadratics in our grade 10 academic math class. So this lesson is sort of the culmination of this unit, and in a lot of ways it ties back into just problem solving in general for our course, our grade 10 academic math course. We're going to do some clawing back from Unit 1, which was solving linear systems. Basically, today's lesson is about developing strategies for problem solving, because it's not easy, but it's easier if we're doing a lesson on optimization and we're doing questions in our homework about optimization. You know you're going to be completing the square to find a vertex. Same thing with solving quadratics using factoring or the quadratic formula. Like, you know that that's how you're going to go about solving the questions presented in those lessons. But what if you didn't have that guidance of the lesson title and knowing the context of what it is that we're practicing? What if it was just a problem and you had to figure it out? So the first page of our lesson is sort of a flow chart that hopefully will guide you in the decision-making process as to how you're going to go about solving any old word problem that shows up. Specifically, we're trying to differentiate between quadratics, where you're going to be optimizing, quadratics, where you're going to be solving, and then linear systems, where you're going to be solving. So let's start with step number 1. Step number 1 says, does the problem contain the word maximum, minimum, greatest, least, etc.? If it does, then that is, as we've said, an optimization problem. You're going to find the vertex by completing the square, and you're on your way. So I just want to add that in here. We're going to be completing the square, find the vertex. We're going to call that complete the square. A little bit more guidance there. Complete the square, and you're good to go. So if our problem includes the phrase or the words max, min, greatest, least, etc., biggest, smallest, whatever, we're going to be solving it like an optimization problem where we are going to find the vertex by completing the square. Okay, so what if your problem doesn't include any of these clue words, max, min, greatest, least? We're going to head over here. Step number 2 says create the equations necessary to solve the word problem. So that's the part where you would make equation number 1, equation number 2, ... And then we're going to look critically at those equations and ask ourselves, what is the highest degree found in the equations that you've created? Remember that anything to the exponent 1 is degree 1, and anything that has a higher value is going to be degree 2. That would also include something like xy, which is also a degree 2. So if the highest degree found in the equations you've created is a degree 2, which we'll look at over here, so degree 2 tells you that it's going to be a quadratic word problem. So you're going to start with substitution, and again I want to make a little note here that the substitution we're going to make is linear into quadratic every time. Linear into quadratic. Quadratic. Whoops, that's not how you spell it. Quadratic. And then you are going to solve using either one of these methods that works. Factoring, again, we can use the discriminant to tell us if that's the right approach, or the quadratic formula, which will work every time. What if the first degree, or a degree 1 function, is the highest degree that you have in either of the two equations that you've created? Then we've got a linear word problem. We're going to use substitution or elimination to solve. And as I said, this is a bit of a callback, right? So this is a review from lesson number, or unit number 1. Unit number 1 deals with solving linear systems and linear word problems. So if you are trying to remember how to do substitution and elimination, you can head to Unit 1. Now I will say that as a sort of a shout out or a reminder about Unit 1, we looked at 6 different types of linear word problems, but we only focused on 3 of them. It was relative number problems, age problems, and break-even problems. That was it. That was the third one. So we looked at 3 types. In this unit, we're going to be looking at 3 other types of linear word problems you might encounter. So hopefully this flow chart helps you. Again, we're looking for, I'm going to model it as we do the next 2 examples, but we're looking for max min, and if we don't see max min, we're looking for degree, and that will dictate how we go about solving. All right, without further ado, let's jump in. So a computer software company sells programs to students for $20 each. 300 students are willing to buy them at this price. For each $5 increase in price, there are 30 fewer students willing to buy the software. What price will generate maximum revenue? So I've already set up a little bit of our problem here. The first thing that I notice as I read this is you see the word maximum, which tells you this is going to be an optimization problem. This is step number 1 in us figuring out how to go about finding the answer to this word problem. We see the clue word, it's going to be optimization. We know we're going to be completing the square to get the vertex. Now it might be a good time to pause it, write down the stuff I already have on the screen here, and then we'll proceed from there. Okay, you're back. So this is a revenue problem, and as you'll recall, we determine revenue by multiplying price by numbers of items sold. And when we set up this question, and maybe I'll just erase that and we can I'll just sort of talk you through how I build it. So we know that the price for the computer program is $20, and at that price 300 students buy it. What is proposed is a $5 increase. And every time we do that, 30 fewer students are going to buy the software. How many times are we going to do this $5 increase to get to maximum revenue? That's the unknown piece. That's the variable n that we put in here. Since the number of times we increase by 5 will also correspond to the number of times 30 fewer students buy the software. So there's our setup. Now we are going to work. We're looking for maximum revenue, so we're going to expand out our equation here. So we have our revenue being equal to, so 20 times 30 is going to be 6,000 minus 600n plus 1,500n and minus 150n squared. So now we don't have a substitution for revenue. We're not trying to solve for a particular value. We're looking for the maximum revenue. So we're going to gather together our like terms, and we are going to complete the square. So that's going to give us negative 150n squared. That's going to give us plus 900n and plus 6,000. Okay. So from here we want to complete the square. We do that by common factoring out our a value. So we have negative 150 is our a value, leaves us with n squared minus, I think that's 6 possibly. That makes sense, right? 6n, and there's our plus 6,000 hanging around. So now we're going to complete our square. We are going to create our perfect square trinomial by taking half of b and squaring it. So that's minus 6n. We're going to be adding, so half of negative 6 is negative 3. Squared gives us 9, plus 9, minus 9, and there's our plus 6,000 on the outside. So I say this all the time when we complete the square, but this value here, this value, this plus 9 we've created, or that we've put in, creates our perfect square trinomial. This minus 9 over here keeps our equation balanced. So let's go about factoring. We have r equals, now we need to bust that negative 9 out of the bracket. And I'm going to multiply that by negative 150. So we have 150 times 9, or sorry, negative 150 times negative 9, and that's going to give us 1,350. So let's get this kind of happening all on the same side here. We have negative 150. We have our n squared minus 6n plus 9. Outside that bracket, we have our 6,000, and we have that freed negative 9 times negative 150, which gives us 1,350. So now we simplify and factor. R will be equal to negative 150. And we're going to have something in there, and that's plus 7,350. So we want to find the thing that multiplies to negative 9 and adds to negative 6. So we know the sign in here is going to be negative, and that value will be 3. So our vertex in this case is going to be 3. Let's just write this over here. So the vertex is going to be 3 and 7,350. So again, I do this usually. Let's interpret what this means. So this would be our x our input, that's our output value, so corresponding here to our x value and our output value. So this is telling us that our the number, so the n was the number of increases for us. We're going to be making 3 increases, and the output value is revenue, and that will give us a maximum revenue here of $7,350. So that's really all they're asking us here, I think, is, oh, sorry, they're asking us what price will generate the maximum revenue. So let's go find the price. So the price, as we know, was going to be $20 plus the $5 increase 3 times. That's going to give us 20 plus 15, which is going to give us a price of $35 that leads us to our maximum revenue of $7,350. So therefore, the price for max revenue is $35. There we go. And that is our first word problem. So again, this one here, we tapped out at step 1. We found our clue word maximum, which means it's an optimization question, which means we're going after the vertex. We create our equation for a revenue. That's a price times number of items sold. You have those 2 initial parts, and then there are adjustments made, information provided in the question. We get our standard form version of our quadratic. We complete the square to get to our vertex, which is 3 and 7,350. We look back at the question just to see what it is that we need. In this case, it's asking for the price, so we provide the price. Boom, that's it. Example number 1 is finished. Come on back for part 2, and we'll tackle example number 2.